Hey, welcome back to chemistry. And so we're going to finish off chapter 6 by talking about something new called the standard enthalpy change for formation of compounds. So that's a little bit different than the standard enthalpy change for reactions. And so I need to talk a little bit about the differences between those things. So let's say you have a chemical reaction, and let's say it is the combustion of methane. So that would be CH4 plus O2 gives you CO2 plus water. And so what you can do is you can balance this equation if you wanted to. So I'm going to balance the carbons. They are balanced. Hydrogens, it looks like you need to put a 2 here, so now the hydrogens are balanced. And oxygens, it looks like I need to put a 2 here, and then the oxygens are balanced. So this is a balanced equation. So as you know, this reaction, when it happens, is an exothermic reaction and releases heat. And so the heat release is associated with a enthalpy change for this reaction. And so what you can do is to indicate what the enthalpy change is, you write delta H reaction. And I think, as I recall, the value is negative 890 kilojoules per mole. So there's probably nothing really new here. And so you know, for example, that if you have this chemical reaction and if it's releasing heat, it's releasing energy in the surroundings, then the delta H will be negative. On the other hand, if you have a chemical reaction which is absorbing energy, then the delta H would be positive. So far so good. Now I'm going to talk about a particular kind of equation which has a slightly different change of enthalpy symbol associated with it. So let's say that you are forming a compound like magnesium carbonate from its elements. So I will write out what the elements here for magnesium carbonate are in just a second in the balanced equation. But let me talk about what the delta H may be. It's going to be a little bit different. If we're talking about the formation of 1 mole of compound from its elements, then the enthalpy change associated with that is called the enthalpy change of formation for that compound. And so it will be a delta H, not so much reaction, but an F, even though it really is a reaction. Okay, so why is it called the enthalpy of the formation? Again, it's because we're describing sort of a hypothetical reaction that occurs when you bring the elements that this compound is made of, and then you form the compound. You're looking at the change of enthalpy for that process. So the 3 elements you're going to bring here to form magnesium carbonate are magnesium plus carbon plus oxygen. Okay, so now we sort of have to balance this equation a little bit, and this is a little bit different than the equation up here. So up here, we were basically just adding coefficients just to make sure that for each element, the number of atoms was the same on the left and the right side of the equation. The balancing is similar here with one important difference, in that when you look at this product compound here, you can only have 1 mole of this compound. You can never put a 2 here for this compound, or a 3, or any other coefficient. It must always be 1. And the reason is the enthalpy change for the formation has been defined for the formation of 1 mole of this compound. So we must have a 1 here. So when we do balance the compound, the elements that it's made of are to the left of this, and so we will have to balance this. And so we will have to keep this as a 1, and then the coefficients here on the reactant side, we have to change such that this, the formation of 1 mole of magnesium carbonate is maintained. So how do we do that? So we have magnesium, carbon, and oxygen are used to form this compound. Now what we have to do is we have to use elements in the states they are found in nature. So magnesium in nature is found as a monatomic element. Carbon in nature is found as also monatomic. But you kind of know by now that oxygen here, in nature, you don't find it as single oxygen atoms. If it is pure oxygen, it's always 2 oxygen atoms stuck together. Okay, so now let's check to see if this is balanced. Again, we cannot change this coefficient here for magnesium carbonate, it must stay at 1. So the only way we can balance this equation for this equation here is to adjust the coefficients in front of magnesium, carbon, and oxygen. So we have 1 magnesium in the products and we have 1 magnesium in the reactants, and so that's balanced. We have 1 carbon in the product, 1 carbon in the reactant, that's balanced. Now let's look at oxygens. So we have a little bit of a problem here. So you can see we have 3 oxygens here in the products here, but only 2 oxygens in the reactants. Now again, it would be great if I could put, say, a 2 here in front of magnesium carbonate and a 3 here in front of oxygen, but I can't do that because the magnesium carbonate, if it's, again, a change of the enthalpy for formation, which is in reference to 1 mole of magnesium carbonate, I have to keep this at 1. So I have to, if necessary, add a fractional coefficient to get these oxygen atoms to balance. So I have 2 oxygen atoms here. So how would I get that to balance? Okay, so what I can do, again, is add fractional coefficients. And so one thing that will probably work is a 3/2. And so let's talk about why 3/2 will balance the oxygens. So when you see O2, we have 2 oxygen atoms. So you can think of 2 oxygens, 2 O's. Divide that by 2 here in the denominator of the fraction, down you're down to 1 O, but then you multiply it by a 3 up here in the numerator, and so in the end, then you'll have 3 oxygens here on the left and 3 oxygens here on the right, and so it's balanced. So this is a perfectly good balanced equation to describe 1 mole of the formation of this. If you're looking at, again, the energy associated with the formation of either 1 mole of a compound or an element is called the the enthalpy change for formation. Now, what we can do is we can carry out these reactions in standardized conditions. And so what may happen is that you might have various labs throughout the world who are carrying out this reaction, and they want to use all the same reaction conditions every time they do it and compare the results they get. How much heat is absorbed and released in this reaction, with all the conditions between these different places where this is being tested being the same. So if you want to indicate that this reaction was carried out in standard conditions, what you do is you write delta H of formation again, but to indicate that the conditions are standard, you put a degree sign just to the upper right of the H. And so if you see a degree sign here, that indicates that you're looking at the energy, the enthalpy change under standard conditions. And so what are standard conditions? So for example, if you have gases, they're going to be at 1 atmosphere. And if you have solutions of compounds, they're going to be in 1 molar concentration. Now, usually under standard conditions, the temperature is not yet defined. And so if you're doing this at a particular temperature, a lot of times these experiments are done at 25 degrees Celsius, which is a little bit above room temperature. 25 degrees Celsius is 298 degrees Kelvin. So if you're doing this kind of reaction here to measure the enthalpy change of formation for this compound, and you're doing it at 1 atmosphere pressure with solutions that are at 1 molar concentration and at 298 degrees Kelvin, which is 25 degrees Celsius, then you would write as follows, that whatever you measure the enthalpy change to be for the formation of magnesium carbonate, to indicate that this was also done at 298 degrees Kelvin, which again is 25 degrees Celsius, you put 298 there. Okay, so what we're going to do is, I've kind of mentioned here what standard state is at this point, and so I've kind of mentioned there also that you have to indicate temperature. Now, one of the things that I need to sort of talk about right now is what are these values that you will see for the standard enthalpy change of the formation of whether it be elements or compounds. And so what you can do is you can look at this table, and what you'll see on the left side are listing of either elements or compounds. So for example, we have an element here that I've kind of boxed in red, and so the element is silver. And so you can see there is a value for it, for the standard enthalpy change of the formation of silver in the solid state, and that value is 0. And what chemists have decided to do is they have decided to make the enthalpy change for the formation of elements to be always 0, so that we can compare the enthalpy changes for compounds to them. So for all elements, or rather I shouldn't say all elements, for most of the elements that are found in this table, the standard enthalpy of formation is set to 0. Now, one way to sort of think about this, again, this was set by chemists for a reason, to compare what the standard enthalpy changes for formation of compounds would be. So for elements, you can sort of, because it's set to 0, we can sort of think of this as sea level. So when you do look at the standard enthalpy changes for the formation of a compound from its elements, what you'll see is that they're usually negative numbers. So for example, if you're looking at the standard enthalpy change for the formation of silver chloride, which is underneath silver, what you can see the value there is negative 127 kilojoules per mole. And so what that indicates is that silver chloride, when it forms from its constituent elements, which are silver and chlorine, what will happen in that reaction, energy will be released. And so the reaction is exothermic, and if that's the case, the standard enthalpy change should be negative value, and it is. And so what you'll kind of see is, once again, because all the elements, the standard enthalpy of formation is set to 0, compounds always are negative numbers, and there's a specific reason for this. And the reason is that when you have free elements, they have relatively higher energies or enthalpies. But if you stick elements together to form compounds, like for example silver chloride, which has a negative value, the compounds formed from the elements have lower enthalpy values. And so that results in a delta HF, which is going to be negative. Okay, so one of the things I've sort of shown you here is I've just kind of rewritten what I was just kind of describing on the board. So we can just note again that here we're looking at the enthalpy of formation of magnesium carbonate from its constituent elements. And so magnesium is in the solid state, carbon is in the solid state in the form of graphite, and then again there's oxygen. And because the natural state of oxygen is O2, we have to put a 3/2 in front of the O2 to balance the oxygen atoms. So the delta HF is equal to negative 1,112.9 kilojoules per mole. And again, this is per 1 mole of magnesium carbonate formed. So again, note that the reaction is shown for 1 mole of product. So again, we didn't balance this by, say, increasing the coefficients from magnesium carbonate. That was set to 1, and we had to balance the reactants based on that. So what I want to do is I want to write out some correct thermochemical equations that show the standard enthalpy of formation for various compounds. So let me do that now. So I will go to the board. Okay, so the first thing we want to do is write out the correct thermochemical equation that is used to describe the standard enthalpy of formation for water, which has a value of negative 285.8. Okay, so the first equation I'm going to write here on the board is not correct. I'm just writing this as to be used as a comparison. So I'm going to prepare right now a balanced equation for the formation of water from its elements. And so you probably can do this as well based on what you know. And so you know, for example, we're looking at the formation of water, which is formed from its elements oxygen and hydrogen. So we have hydrogen here plus oxygen here gives you water. Okay, so what I'm about to do is I'm going to balance this equation correctly but for a particular reason, that balancing does not apply to the standard heat of formation for water. So let me just, again, balance it as we know how to do it. So we have 2 hydrogens here, 2 hydrogens here, that's balanced. 2 oxygens here, 1 oxygen here, that's not balanced. So we put a 2 here. The oxygens are now balanced, and we put a 2 hydrogen in front of the hydrogens. Now, we do have a correctly balanced equation, but again, we cannot use this particular balanced equation to describe the standard heat of formation for water. And the reason is, when you write that equation, it must be for 1 mole of water. That's what the standard heat of formation applies to, the formation of 1 mole of compound. So we can't use this. So we have to erase that. Okay, so let's try it again. Let's write a correct equation to describe the standard heat of formation of water from its elements. So the elements again are hydrogen and they're oxygen, like we had before, and they're forming water. Now, again, what we have to do when we change the coefficients here is we have to keep the water coefficient set to 1, because again, we're looking at the standard heat of formation for 1 mole of this compound. So this must stay at 1. So H2 is fine. We have 2 hydrogens here on the left, 2 hydrogens on the right. How do we handle oxygen? Well, we have 1 on the right here. We have 2 on the left, so we're going to have to add some kind of fractional coefficient. So we're going to have to put a 1/2 here in front of that. And now 1/2 times 2 oxygens is 1 oxygen. So we have 1 oxygen on the left, 1 oxygen on the right, and so the oxygens are balanced. Okay, so now what we can do is on this line, what we can sort of do is indicate what the energy change of the reaction is. And so this is written for the formation of 1 compound of 1 mole of water from its elements. So we can write delta H degree F and is equal to that value, negative 285.8 kilojoules per mole. Okay, so this is a perfectly good thermochemical equation for describing the standard enthalpy change of formation for 1 mole of water. Okay, so let's move on to the next one. Okay. So write out the correct thermochemical equation that is used to describe the standard enthalpy of formation for calcium carbonate, which has a value of negative 1,206.9 kilojoules per mole. Okay, so again, what we need to do is write up a balanced equation that describes the formation of 1 mole of this compound. So it's going to be calcium carbonate. So it's going to be CaCO3. Now, again, I can't really adjust the coefficient here because it's for the formation of 1 mole of this compound. So what I do is write out the constituent elements here, which are calcium and carbon and oxygen. Okay, so it looks like calciums are balanced. 1 calcium here, 1 calcium here, that's balanced. 1 carbon here, 1 carbon here, that's balanced. And so we have 2 oxygens on the left here. We have 3 oxygens on the right. And so we need to balance that, but again, we cannot adjust the coefficient here in front of calcium carbonate because we have 1 mole here, and that's what it has to be if we're describing the enthalpy change of formation for this 1 mole of compound. So we can only adjust the coefficients in front of oxygen. So we have 3 oxygens here, 2 oxygens here. So I think we can sort of solve our problem by putting a 3/2 here. So let's think about why that works. And so we have 2 oxygen atoms here, divided by 2 is 1, times 3 is 3, which matches the 3 oxygens over there. So that appears to be a balanced equation that is appropriate for the 1 mole of this calcium carbonate. So now we have a standard heat of formation associated with that. So it's delta H degree F, and we have a value there which is negative 1,206, 0.9 kilojoules per mole. Okay, so this is a good thermochemical equation for this, and so this is fine. So we will move on. Okay. Okay, so what you can do now is, now that you sort of understand what the standard enthalpies of formation are, you can use these values for each of these compounds that you can just kind of figure it out how to write equations for. you can use these values, which you usually get from a table, to find the standard enthalpy change of certain reactions. And so what you would have to do is that, as I say there, is that the change of enthalpy for the formations can be used to find the change of enthalpy for the reaction according to the following equation. So if you want to find the enthalpy change for the reaction, what you have to do is add up all the standard enthalpy changes for the formation of all the products only after you multiply them by their coefficients. So you'll get a number for that. And then what you'll have is you'll have done the same thing for the reactants. You'll add up the standard enthalpy change for formation of the reactants. And then each of those will have coefficients associated with them, and you multiply by them. And you take those two values and you subtract the value, the total value for the reactants from the total value of the products. So here's sort of an example problem. So I think the best way to sort of do this is to do this with an example problem, because it's not, I mean, once you sort of see how to do it, it's not so bad. Okay, so ethanol is used as an additive in many fuels today. What is the enthalpy change of the reaction? That's actually the standard enthalpy change because there's a degree sign there for the combustion of ethanol. Okay, so I think it may not be a bad idea for me to rewrite this equation. So it's 2C2H5OH plus 6 oxygens gives you 4 CO2 plus 6 H2O. Okay, and so what we're trying to find in the end is the standard enthalpy change of this reaction. So the information we're given are the standard enthalpy changes for the formation of each of these compounds here. And so we have to take those numbers and then, using that formula that we just saw, figure out what the standard enthalpy change of the reaction would be. So the equation, as I recall, is the standard enthalpy change of the reaction is going to be equal to the summation of N, which is a coefficient for each of these molecules, of the standard enthalpy change of the products, and they're all added up, minus the sum, and this is M, of the standard enthalpy change for the reactants. Okay, so let's go ahead and see if we can solve this problem. Let's see if I can get a better pen here. Okay, so this is what you do. So let's first look at the products here. And so you'll notice that we have carbon dioxide and water as products, and we have 4 moles of carbon dioxide formed and 6 moles of water formed. And so what we want to do is we need to look up in that table the standard enthalpy of formation of carbon dioxide and multiply by 4. And then take the standard enthalpy of formation of water and multiply by 6, and then add that together. And that will take care of those products. So let me just go ahead and do that. So to solve this for the product side, so we need 4 of the standard enthalpy of formation of carbon dioxide. And so we have that in that table there, which is negative 393.5. I'm going to leave out the units just to make my life a little bit easier. Plus 6 times the standard enthalpy changes of water. So it's going to be 6 and then of water. Now be careful. So the state of the water is pretty important here. So this is in the liquid state and it's not in the gaseous state. And so we have to sort of make sure that the standard enthalpy of formation we look up is the correct one for water in the correct state. So we don't want the enthalpy of formation for water as a gaseous state. We want it in a liquid state. And so it's going to be negative 285.8. Okay, so here is sort of the product term. Okay, so we'll have to subtract that here from the sum of the enthalpy of formations times their coefficients of the reactants. And so I'm going to put that down here. Okay, so one reactant that we have is ethanol here, C2H5OH. And so you can look up the standard enthalpy change of formation for ethanol, and it's negative 277.6 kilojoules per mole. And there's 2 moles of it. So I'm going to put a 2 here like this. And then we put in the enthalpy change, which is negative 277.6. Okay. Now, what about oxygen? So what you'll notice is that we have oxygen here as a reactant. So you say, oh, okay, well, I need the standard enthalpy of formation of oxygen. And so it's not listed in the table. And the reason is because oxygen is an element. Its standard enthalpy of formation has been set to 0. So if you have an element and you're looking at a problem and it doesn't appear to be in the table, I think you can safely assume that that enthalpy of formation is going to be 0. So I'm going to put plus 0 here. Okay. So I think you can go ahead and work out the math, and I think in the end the value you will get when you do the math, if you do it pretty carefully, is negative 270,732 kilojoules. So what is this again? So again, we were using these standard enthalpies of formation to find a standard enthalpy change for the reaction. So in the end, what we had just found by considering the standard enthalpy of formations for each of these compounds in the formula, we're finding the standard enthalpy change for the reaction, and it's that value. Okay, so let's move on to one more. Okay, so we have one more. See if we can, there we go. Okay, so we're going to do one more remaining problem. So we have a reaction of benzene with oxygen to produce carbon dioxide and water. So let's write out the equations. So it's 2C6H6, which is benzene, plus 15 of oxygen gives you 12 CO2 plus 6 H2O. Okay, so what we want to try to do is from the standard enthalpy of formations, we want to try to find how much heat is released per mole of benzene consumed. Okay, so what we're going to do is first, considering the standard enthalpies of formation, what we're going to do is find the standard enthalpy change of this reaction here. And then from that, figure out how much heat is released per mole of benzene. Okay, so what we have to do to find the standard enthalpy of this reaction as written is we have to add up the standard enthalpy changes of formations of the products multiplied by their coefficients. So it's going to be 12 times negative 393.5 plus 6 for water, and the standard enthalpy of formation of water, liquid water, is negative 285.8. Okay. And so that takes care of the products. Now let's look at the reactant. So it's going to be 2 of benzene here, 49.04. Okay. So let me just go ahead and work out the math really quick and see what we get. So it's 393.5 times 12 is negative 4722 plus 6 times negative 285.3, 285.8 times 6 is negative 1714.8. Okay, so that's adding them. So we'll add those numbers in a minute. And then it's 49.04 times 2 is equal to negative 98.08. Okay, so let me go ahead and add these two numbers up here. 4722 plus 1714.8 is negative 6436.8 minus 98.08. So that should be, I get, as the standard enthalpy change of this reaction to be 6534.88 kilojoules. Okay, so we have to be careful here. So this is standard enthalpy change of the reaction for the combustion of 2 moles of this benzene. but we don't really want that as the answer. As we want in the answer, we want to know how much heat is released per mole of benzene. Well, what we can do is, what we can figure out is we can say, well, if this amount of kilojoules is the enthalpy change for 2 moles of benzene, what would it be for 1 mole of benzene? So you'll take this number and divide it by 2 moles of benzene. So it's divided by 2. And so I get 3267.44 kilojoules is the standard enthalpy change for benzene per 1 mole of benzene. The symbol for benzene is, or abbreviation for benzene is BZ. Okay, so I probably need to be a little more careful about my signs. This is a negative sign here. It's a negative sign here. So what is the heat released per mole of benzene? So this is the standard enthalpy change per 1 mole of benzene. This is also the heat released by 1 mole of benzene. So the answer is that Q for 1 mole of benzene is just that number, which is negative 3,267.44 kilojoules, which is released per 1 mole of benzene. So that should be the solution. So thank you for listening, and we'll see you next time.